Oh, wait. All right, so welcome back to another fun-filled day of differential equations. Before we keep on our discussion of Laplace transforms, I'm just curious if there are any homework questions you guys have. Let me just put out, I totally forgot, big surprise, to post the new homeworks that I said I had. So I just wrote it down on my notes as a no, do it today. So yes, other than where the hell is the homework set for the next couple of sections. Any questions about how we're doing? We doing all right? Tired of series stuff?
It's a lot of writing.
Yeah, it is. And it's
checking, making sure every step is done correctly. It's not hard, it's just work.
Yeah, this is one of those places that being detailed oriented,
yeah,
right? That's huge. So you have to pay attention to every little thing and make sure that, you know, when you shift, you change everything in your shift and all that. So yeah, no doubt about it that it's definitely one of those things where precision is key. So, but in general, we're feeling okay with the with how it's set up. So Wes, you just said, will it be due on Friday? You mean the next set? Yeah, probably not. Like everything else at this point in the quarter, I start not really caring, especially about homework. So, well, yeah, I think we'll adjust accordingly. Because especially if I don't get it posted until tomorrow or late tonight, I don't want to give you just like 24-hour kind of turnaround. So, yeah, anticipate that we'll just make the next due date Monday, but it might be like a double set or something. So. Okay, well, then hearing no real questions about the homework, let's just kind of remind you where we've been. So we just looked at how we can use series to help us find solutions. And so you see that it works. It totally works, but like Ian was saying, it's a grind. And so obviously if we can do other things, we want other things. So where we're heading now is the Laplace transforms. And I introduced them to you last time, but I didn't really tell you why. So let me give you a little bit of why, because you know I like doing that. So a little bit of the why behind Laplace transforms is that this is going to be a method that we can use to solve differential equations that's going to turn it into algebra. Now, I know most of us are not huge fans of algebra, and you go, yeah, that's not better. But I think we can all objectively say that if you can get things to just algebra, we're pretty set, at least compared to calculus, because there are a lot of things we just can't integrate, or when we differentiate, they just become so gnarly, it's terrible. But with a little algebra, we can simplify it. You've seen that, like when we use logs, for example, to sort of simplify things up. And that's what Laplace transforms are. This is going to turn differential equations into something that's just an algebra question. So that's where we're going with this. And I apologize for not telling you that last time, but just so you know, there's a reason. So let's get back to what Laplace transforms are and what they look like. So I'm going to switch to the board just to write some stuff and remind you. So, sorry about that. All right, so just to remind you about the Laplace transform, all we do with a Laplace transform is we are taking a function, we're putting it into our Laplace transform. So we'll have L of f of t, and literally all it's saying to do is to integrate from 0 to infinity e to the minus st times f of t dt. Okay, so that's it. That is it. All we do is we take a function and we integrate this. So we saw some last time. Let me just remind you of the ones that we did last time. Actually, let's do one more. Let's do this. Let's do the Laplace transform of t. So this would be the function f of t equals t. So y equals t, good old linear function. So we just integrate from 0 to infinity t e to the minus st dt. So we saw that these are improper integrals, these guys that have the infinite bound. So we need to make sure that we actually can get convergent values. So it sort of specified some values of s that are going to work. But basically, let's go ahead and run this. Let's find this integral. So if we were going to integrate this one, we'd have to integrate by parts, right? This is that good old u times dv business. But of course, we're just going to make use of the of our technology, right? So if you integrate t times e to the minus st, let me just go ahead and do it here on my calculator because I'm way too lazy to try to do it today. Otherwise, what you end up with is a minus t over s times e to the minus st minus 1 over s squared times e to the minus st. And we're going to evaluate that at 0 and infinity. Okay, so obviously the 0 bit, that's really easy to plug in and get. We get minus 1 over s squared that we're subtracting, right? Because the t over s, that goes to 0. And then this one, the e to the minus st, that's e to the 0, which is 1. So we got minus 1 over s squared. Now, the other piece, in order for this to converge, we are going to have to put a requirement on this that s is greater than 0. And as long as s is greater than 0, then we know that the e to the minus st is going to drop to 0 as we go to infinity. So if those things drop to 0, of course, that gives us zeros all around. And what we're left with is 1 over s squared. All right, so there's a real quick example of how this is done. But the Laplace transform of t, well, when you do that, you put in t and you get out 1 over s squared. So we really have, I think, 3 that we've done now, right? Because last time I showed you 2 of them. I showed you a constant function. And then I also showed you, I think, e to the at. We did a generic exponential. But you can basically make a list of all kinds of functions and then what their Laplace transforms are. So we could even make a chart here. And so here are the ones that we've seen before. So last time we did a constant function, and we saw that that constant function gave us c over s. I just did t, and that gives us 1 over s squared. And then we also did last time e to the at. So I think we just did a generic exponential, e to the at. And that gave us 1 over s minus a. But with each of these, we did have some restrictions on s. Like for the first one, we had to have s was greater than 0, just like we did here with the t. And then I don't know if you remember this, but with the e to the at, we saw that s had to be bigger than a. And all that stuff that I wrote in blue really is just a, those were the conditions that were required for these integrals to actually be defined, for them to converge, right? So there's no point in having some sort of an infinite integral if it's not going to actually go to a number and give us a value. All right, well, we're going to add to this list. We're going to do some more today as we go, but I mean, hopefully you're seeing that it's just the same process. You want to do sine, okay, put in a sine, so you integrate e to the minus st times sine of t.
that's another one you'd have to use integration by part. Or, okay, we want a cosh. All right, so e to the minus st times cosh. You want a natural log, e to the minus st times natural log, and so on. So we literally can do a Laplace transform for any function, but what we get out, it's just a matter of what the integral actually gives us. Okay, so hopefully you're kind of good with that real quick review of what Laplace transform is. So let's go a little bit into the theory of Laplace transforms. Okay, and this theory is going to help us when it comes time for us to do differential equations. So here's the first thing that I'm going to give you. I call this a fact. I guess you could call it a theorem, but I feel like just saying that this is a fact. All right, and that is that the Laplace transform this is a linear operator. So from linear algebra, I'm sure you guys remember what that means, right? If you take a linear combination of functions and you put it in a Laplace transform, you get the same thing as the linear combination of the Laplace transforms. So basically, if we were to do L of, say, F plus C times G, that's going to equal the Laplace transform of F plus C times the Laplace transform of G. So basically, addition and scalar multiplication, this thing goes over both of them. Okay, so I wrote that as a fact, and I think like any fact, we need to justify it. Do you see why this must be?
Well,
Why does this have to be a linear operator?
the integral is a linear operator. It's a linear operation, and it doesn't change
I
much.
think you could probably stop there, right, Dia? Where you go, well, integrals are linear operators, and if all we're doing with a Laplace transform is taking an integral, well, there you go, right? So that's why I didn't actually like put theorem and let's prove and all that, because it's sort of a, well, yeah, duh, follow-up to the fact that that's what integrals are. And yes, we're multiplying by that e to the minus st, but we already know that multiplication distributes through over addition and, you know, blah, blah, blah. So really the reason that this is true is because integration itself is a linear operator. Okay, so hopefully you're convinced by this fact, and you know, yep, definitely, we got that. Now, why this is useful is, well, in lots of regards, and you'll see specifically with differential equations. But one of the things that we can do with this is actually tackle things like functions that might seem a little bit tough or hard to integrate. We can actually use this fact to simplify it to help us find the linear or the Laplace transform for them. So an example of what I'm talking about, and I apologize for erasing the chart, but you know, these things happen, I need some space. Let's say we want to find the Laplace transform of sinh. So easy enough, right? Okay, well, so that's the integral from 0 to t, or sorry, not 0 to t, 0 to infinity of e to the minus st times sinh of t dt. And yes, with our technology, I mean, I can just grab my T89, punch that in, do its thing. But alternatively, we can use the definition of sinh. I don't know if you remember this, but sinh and cosh are built off of exponential functions. I'm seeing a couple of like head nods and, oh yeah, I kind of remember that that is the case. Here's actually what sinh looks like. So sinh, it's the same as e to the t minus e to the minus t over 2. So that was the definition back in the day. And before I go too far, I'm actually going to change this so that this is sinh of AT. I want to be able to have just some sort of a number in there. So all that changes is the fact that these exponents now are e to the AT and minus e to the minus AT. But that was definition. Okay, but now let's use the fact that the Laplace transform is a linear operator. That means that this is going to be the same as 1/2 times the linear operator of e to the AT minus the Laplace transform of e to the minus AT. And those we can get pretty fast. In fact, we've already done e to the AT. We saw that that was 1 over s minus a. Now, e to the negative AT, we can actually use the same Laplace transform. We just change that a to a negative a. So obviously, subtracting a negative a is the same as adding. So this becomes 1/2 times 1 over s minus a minus 1 over s plus a. Well, let's just do a little bit of work on that. If you get a common denominator, you end up with a 2a over 2 times s minus a times s plus a. The 2's cancel. And we get a over s squared minus a squared. So there's the Laplace transform for sinh. And you can even see how this was way faster than trying to do the integral itself. And also, if you think of this historically, and sometimes it's good for us to kind of try to put ourselves into, into the shoes of the people that were doing this. So go back to when Laplace was around. I think Laplace was 18th century. If not, he was early 19th. But so we're talking, right, hundreds of years ago, at least 200, maybe 250, something like that. And they didn't have all this lovely technology that we have. And so trying to integrate this e to the minus st sinh of AT business would have been gnarly. But instead, recognizing that, oh, I can split it apart into something that was easy, right? E to the AT was easy. We did that without even thinking about it. And then we were able to use that to figure out sinh. So you can see why this was kind of a big deal and how even more complex things can be formed by using the fact that it's a linear operator. So that's probably one of the reasons why he chose to use an integral. I don't really know the history of the Laplace transform, but I'm going to guess that he used an integral operator just because we already know that integrals are nice in terms of being linear and whatnot. All right, so again, remember we do have to worry about s's. We already know that s has to be greater than a for the e to the AT, right? When we derived that, we saw that that was the case. But there's also going to be a restriction because of this other one. And in this case, it's kind of similar. It's just now we need s to be greater than negative a. So you kind of get the same sort of deal, but you can kind of lump this together, and that's what we will do. We'll make it just one statement. And what this says, if we were to kind of combine it, is that we would need the s has to be greater than the absolute value of a. So that takes into account the negative business as well. So anytime you do a Laplace transform, not only do you find what that value is, but you also have to state when we're good. What are the conditions on S? All right, so cool. S is a linear operator. We can make use of it to help us find other Laplace transforms. Okay, so here's your next theorem. And this one we will definitely prove. I mean, I guess we kind of proved linear operator, but it was sort of a duh. But here's our next fact, our next theorem, and I call this the shifting theorem. All right, and so basically what this says is suppose that we've got some function that is the Laplace transform of the function f of t. Okay, so I'm just going to call it big F. Do not get that confused with the antiderivative. I know that we often use that notation. I'm just calling this guy big F because it's related to little f, but it's the linear, or the Laplace transform, little f. Okay, so then suppose that we were to shift this. So I'm going to shift it just some distance away. So we're going to do a horizontal shift. Well, that's the Laplace transform of another function. And what that function is e to the at times f of t. So what we're doing, this shifting theorem, we're not shifting the original function. We're shifting the Laplace transform. Okay, so that's what's going on here is we're shifting the Laplace transform. And what that does is causes us to take the function whose Laplace transform is what we're starting with, and we multiply it by e to the at. Okay, so let me prove this to you, and then I'll show you how we can use this. All right, so here comes your proof. And to prove this, I'm actually going to go to the definition of the Laplace transform. So we know that f of s minus a, well, that integral from 0 to infinity of e to the minus s minus a times t times f of t. So I'm basically just substituting it in, right? Instead of s, I'm changing it to an s minus a. Now, I can use my rules of exponents to split this up. So I get e to the minus st times e to the at times f of t dt. And notice that if I just kind of lump that stuff, this stuff together, this is the Laplace transform by definition of e to the at times f of t, right? Because Laplace transform just says multiply by e to the minus st and then integrate. So it's a pretty easy proof. It really isn't that complicated. So let me just show you then how we would use this. All right, so basically here's my question. What function, or Yeah, let's do it this way. So what function has a Laplace transform of, and let's go with f of s equals, and we'll go with a over s squared minus 3s. No, not 3, 4s plus 4 plus a squared. Minus a squared. God, I'm sorry, guys. Okay, so basically what we need to do is see if we can find a function whose Laplace transform we know that looks a lot like this, that's just been shifted. All right, well, it probably isn't going to surprise you. We're going to complete the square on this. So we're going to get a over s minus 2 squared minus a squared. And that should look kind of familiar because we did one just like this a minute ago. And that was sinh, right? Because what we know, the Laplace transform of sinh, that was equal to a over s squared minus a squared.
It's just
So
shifted to the left then.
So it's just
I mean,
been
to the right.
shifted to, exactly. So that means that this function that gave us that Laplace transform, it's actually going to equal e to the minus 2s times sinh of at. Sorry, I put minus, it should be plus 2. And I put an S there, it should be a T. God damn it. Like I told you, I'm having one of those days. All right, so really the goal with this is that even if your form isn't quite what you know or quite what you're used to, if we can get it close and we can see that there was actually a shift, it is possible to figure out what that original function was by just throwing on the e to the at, whatever that happens to be. Okay, so this is a shifting theorem. And where we're really going to use this is in a little bit when we start dealing with piecewise functions, because I'm sure you can kind of see how this might help with piecewise functions. If a function turns on, say, out at x equals 4, we want to be able to shift it over 4, and that's what this will do for us. Okay, so a little bit more theory here for shifting theorem. All right, well, here's another fun fact for you. So we'll call this again fact. The Laplace transform is 1-to-1. Okay, so Laplace transform is 1-to-1. So think about what that means. Given a function, obviously when you do the Laplace transform, you get some, formula in terms of S. But the fact that it's 1-to-1 says that if you get that formula, or whatever the Laplace transform is, it comes from only one function. Okay, so what do you think about that? I mean, obviously it's not as easy to prove as it's a linear operator because we can't just go, well, it's an integral.
Pretty nifty, I guess.
Yeah, does it feel okay?
Yeah.
I can accept it. Mm-hmm.
Okay, well, you can accept it, okay. But we should never just go with the, yeah, it feels good, let's do it, right? That's always gonna get you in trouble in math. But let's kind of like reason it out. Now, something that should make you a little bit nervous about this is think about what's happening. A Laplace transform is the result of an integral. Okay, so basically we're going backwards from integration, right? Or that. And think about integrals. Integrals add in a plus c. So we've already seen that, like, if I give you a derivative, you don't necessarily know the function off, that it's just itself. And that's kind of something that we need to worry about. But the big difference is that these integrals were, they were definite integrals. They had bounds. And we know that when we do definite integrals, you get a number out. Definite integrals give you a value. So this one is almost as fast as, well, it's an integral. It's a definite integral. So when you have an integral with bounds, when you have a definite integral, what you get is what you get. There aren't ors, there aren't options. Okay, so another fun fact, that the Laplace transform is 1-to-1. All right, well, obviously what that means then is that if you are given a Laplace transform, we can actually figure out what the original function was. So I want to give you a couple more Laplace transforms, some more that are kind of big. And I know that in the text, they keep talking about there's like a Laplace transform list. I have no idea where it is. It's probably in an appendix or something. But my plan is actually to upload one onto the Canvas shell in the files so that you can reference it. Okay, so my goal is to do that in addition to turning on your homeworks. We'll see which one gets done first.
So sort of like an integral table in a sense.
Yeah, that's exactly what it is. That's exactly what it is. So we've already got a few. Let me give you a couple more of them. And these are kind of the biggies. So for example, sine of AT. Right, we're going to see sine a lot. So sine, its Laplace transform actually looks a lot like sin's, except it's a plus on the bottom instead of a minus. Cosine, well, it's s over s squared plus a squared. Yeah, hold on one second, guys. Yeah.
I'm very sorry.
Okay.
They sent Mat204 out. They're burning things in our yard
Okay.
with fire.
Okay.
That's not safe.
Okay. All right. Sorry about that. The joys of moving and dealing with stuff. Anyway, okay, so sine and cosine look like this. We've already got E. Let me just tell you what we get when we have t to the n. So you have any power of t to the n. You get n factorial over s to the n plus 1. So actually, if you go back and you look at what we found for just plain old t, it ended up being 1 over s squared. It does follow that. But it is kind of nice that there's a form for t to the n. And then the other one I want to give you is cosh, just to be complete, because I gave you cinches. So here's coshes. Coshes is s over s squared minus a squared. Which again looks a lot like cinch, but has an s on top. So you could actually derive all of these. I'm not going to bother with it, but I want you to have them just so that we can reference them when we go backwards. Okay, so what we're going to do for a little bit now is practice with the reading from the right and going to the left, starting with the Laplace transform and figuring out what the original functions themselves were.
Hey Bruce, I have a question.
Yeah.
With sine of at, is that in the denominator s squared plus a squared?
Yes.
So both of them are the same for sine and cosine?
No, cosine has an s on top.
Oh, I got it. I see.
Yeah. But it is interesting that the sinh and cosh forms are exactly the sine and cosine forms, but with a minus on the bottom instead of a plus. A lot of intertwining interactions between all these different functions. Okay, so let's go the other way. Let's take some functions and see if we can go in reverse and figure out, or some Laplace transforms, I should say, go in reverse and figure out what their functions originally were. All right, so let's start with one that's not too terrible. Let's say we've got f of s is equal to 3 over s squared minus 4. Okay, so the goal is to look at that and see which of the forms does that look most like. So of all the functions that we've talked about, which of those forms does that look most like?
Cinch, I'd say.
So Thea suggests cinch. Think about what cinch was. Cinch was a over s squared minus a squared. And I would agree. I'd say, yeah, that's pretty close to cinch.
Yeah.
Because we know that the cinch of 2t would be 2 over s squared minus 2 squared.
Yep.
Right? Which would be 2 over s squared minus 4. So we're pretty close. But of course, we've got a 3 on top instead of a 2.
Mm-hmm.
Well, that's actually pretty easy to take care of. Because if you think about it, if I want to change this 2 to a 3, I'm just going to multiply. And I'm going to multiply by 3 halves.
Oh.
Right? So that's a constant multiple. And we already saw that these are linear operators. So that tells me that the function that we started with then, so f of t, is going to be 3 halves sinh of 2t. So it's all about recognizing the form and going, oh, I know something that looks like that, and running with it.
So pattern recognition really factors into this.
Oh, yes. It's all about pattern recognition. Okay, but you want to look on the right-hand side of your chart and see which of these does it look like. Now, like this one, you're not going to get exact, not going to look exactly right, but if you can be off by a scalar multiple, for example, that's beautiful because of the fact that these things are linear operators. So if you want, sometime go ahead and do the Laplace transform of 3/2 inch of 2t, and you'll see that you get this. All right, so let's try another one. It's a little bit more complicated. So let's say we've got f of s equals 2s plus 3 over s squared plus 9. All right, so what about that one?
Am I right that technically you could split those two up and examine their bits? Because one of them looks like what is it? One of them looks like sine of 3t. I'm not sure what the other one would be, but it's yeah.
Okay, and so technically, yes, you absolutely can because they're linear operators. You can always split them in addition and look at each separately.
Mm-hmm.
And not just technically, but that is exactly what we want to do. Let's split this thing apart. It's 2s over s squared plus 9 plus 3 over s squared plus 9. And Thea, you are dead on that this second one most definitely comes from sine of 3t.
Yeah.
That's a over s squared plus a squared. Now the other one looks a lot like cosine.
It's
Right?
just being multiplied. It's just being multiplied by 1/2 then, right?
Okay, so it's double what we wanted, right?
Yeah.
So think about it this way. Let's factor out the 2. So we're going to have 2 times s over s squared plus 9. So the 2 is a constant multiple. So we'll take it along for the ride. So what we get is f of t is equal to 2 cosine of 3t plus sine of 3t. And now that I wrote this one out, I think I had it backwards for that other one. When we multiplied by 3/2, I think we needed to divide out by 2/3.
Got it.
So it's subsequently been erased, so I apologize. I can't go back and look at it. But this one, again, by just breaking it apart, we can figure out what those two are individually. All right, so again, kind of pattern recognition. But then, of course, you get into things like this one. Before I move on, we okay with this guy?
Yep.
That's how it worked. All right. So let's try this. Let's say that we've got 2s plus 1 over s squared minus 2s plus 2. All right, so I ask you, all right, what does that one look like? And that definitely should be, I don't know, it doesn't really look like any of them. So here's what we're going to do. We are going to play a trick. We're going to complete the square. So completing the square is one of your best friends when it comes to Laplace transforms. Let me show you why. Complete the square on the bottom. So we get 2s plus 1 over, well, this is going to be s minus 1 squared plus 1. And this is definitely starting to look like something else we have. Now I know that s minus 1 squared might be throwing you a little bit. So just, you know, rename it or something. It's w squared, ham squared, or whatever. But what kinds of things have a bottom that look like w squared plus 1?
I mean, wouldn't it be a combination like the last one? Because
okay, so it is. It's going to have sine and cosine.
But the s is just shifted.
Yeah, so this is one that's making use of that shifting theorem. We're actually shifting it by 1. So we're going to end up with sine, and we're going to end up with cosine, but we're going to have to shift 1. So I'm going to want to do what I did before, which is split it up. But before I do that, I want to change the top. Instead of having it in terms of s, I want it in terms of s minus 1s. So what I mean by that is I'm going to write the top as 2 times s minus 1 plus 3. Because if we're going to shift it, the bottom definitely suggests we want to shift, I need that top to be shifted similarly. Okay, so now that we're here, let's split it apart. So if I break it into the two pieces, I'm going to have 2 times s minus 1 over s minus 1 squared plus 1 plus 3 times s minus 1 squared plus 1. All right, so those constant multiples, not a big deal. We factor them out. So if we look at the other pieces, this is where we recognize, okay, this one is cosine, but there is that shift by 1. The other one is sine, also being shifted by 1. All right, well, that shifting by 1 is going to introduce an e to the 1t. So when it turns, or when we get down to what it actually equals, this function f it's 2 times e to the t times cosine of t. So the 2 was that constant multiple. The e to the t is because we shifted 1, and it was cosine because that was the form for cosine. And the other piece is going to be 3 times e to the t sine of t. And the 3 and the e to the t are there for the same reasons. The 3 is a constant multiple, and the e to the t comes from the horizontal shift. Okay, so there's that one. So notice that we can pull that trick, completing the square. So watch for that. Completing the square can really help you out. It just means that there's some sort of a horizontal shift. All right. However, you don't always want to complete the square. Sometimes you can get to this a little bit faster and easier. Let me show you. So what if we have f of s equals 2 over f squared plus 3s minus 4? So we could complete the square, but let's not. What else might you be inclined to do algebraically with this other than complete the square? I mean, look at that bottom. There's something you have to want to do on that bottom.
Parts? Oh, wait, no.
Okay. I think where you're going is partial fractions.
Yeah, that's what I meant. Partial fractions.
Yeah, because check it out. That bottom, we can factor it, right? That thing factors pretty easily to s plus 4 times s minus 1. And we totally can do partial fractions on this, right? Make this a over s plus 4 plus b over s minus 1, which when we combine that is a times s minus 1 plus b times s minus 4. So we can figure out what a and b are by plugging in specific values for s and go easy. Remember, the easy ones are like the numbers that make those factors 0. So like if we plug in 4, just looking at the top, that gets rid of the b. We got 3a equals 2. So this actually tells us that a is 2/3. If you plug in 1, the a bit goes away. We get b times minus 3, so negative 3b equals 2. So b is minus 2/3. So what we've got then is that f of s is 2/3 times 1 over s plus 4 minus 2/3 times 1 over s minus 1. Now, the 2/3 notwithstanding, those are just multiples. What are we going to get from 1 over s plus 4? What form gives us that? Well, that was one we did last time. That's an e to the at. Remember, e to the at gives us 1 over s minus a. So this gives us e to the minus 4t. The other one, we're going to get the 2/3 because it's constant multiple. But this is going to give us e to the 1t. So partial fraction decomposition is another thing that we're going to make use of a lot. Because if we can split it into the pieces, we can do each one of them individually. All right, so you can probably already see what's going to be happening here, that this is going to be algebra hell. You're going to have to partial fractions. You're going to have to complete the square. You're going to have to do all that stuff. And there really is no way around it. That's just how it is. Okay, so how are we feeling at this point? Kind of regretting coming to class today?
No, not necessarily. It's
Kind of wishing we could be sitting outside in the sun?
I mean,
Hell yeah.
this is better than power series in my opinion, but
Well, okay, that's not a very high bar though, right? I mean,
yeah.
what's better than power series? Going to the
You said
dentist?
it's like the worst than the worst thing we've learned. It's better than the worst thing we've learned. Woo.
Yeah, right. But
Admit
hey,
it.
I mean,
It's the second
it's
worst.
true. It's absolutely true, but it's pretty algebra intensive.
Yeah.
Okay, but let me get to the next theorem, and this is the big one. This is the one we're going to use when it comes to solving differential equations, and that is what happens when you take the Laplace transform of a derivative. Okay, so this is going to be our next theorem. And basically how this is going to play out is that the Laplace transform of a derivative, it's actually related to the original. It's going to equal S times the Laplace transform of your original function minus f of 0. Now, it probably doesn't surprise you that the Laplace transforms are going to be related, right? Since we're integrating and we're integrating a derivative kind of thing, it kind of makes sense. So it shouldn't be terribly surprising. But this is the relationship. It's going to be S times the Laplace transform of the original function, but then we have to take away f of 0, the function evaluated at 0. Okay, now there is a little bit of a qualifier on this function. Okay, this doesn't always work, but this theorem is going to work if the following are true. Okay, so first of all, f must be continuous. Okay, and f prime must be what we call piecewise continuous. So piecewise continuous, it just means that it can be broken into pieces, but each of the individual pieces are continuous. Let me give you an example of a function that's not continuous, but is piecewise continuous. So like, let's say this is our function, or this thing right here. This is piecewise continuous, right? It's not continuous as a whole because there is that jump, but on the individual pieces, they are continuous. Okay, so there are some conditions, but again, there has to be one more, and that is this. There need to be values, some constants. I'm going to call them, well, let me write the statement first, and I'll tell you what's what. But we have to have that the absolute value of f of t, we have to be able to have it be bounded by an exponential function eventually. All right, so basically we just have to find some sort of an exponential function that bounds this thing. We'll see why that has to be, but eventually this has to happen. So think about lots of functions that you know, like the trig function, sine and cosine. Those things are clearly bounded by an exponential because they're trapped between plus and minus 1. You give me an exponential function, I know that it's going to be bounded by an exponential. I just make it bigger. Polynomials, I know, are bounded by exponential functions because exponents grow faster than polynomials, and so on and so forth, and all that good stuff. Okay, so we know that this is true, or we also have that this is going to have to be true. All right, so these are the conditions for it to exist, and for this to be the result is that f has to be continuous, f prime has to be piecewise continuous, and this f has to be bounded eventually by an exponential. All right, so let me do this for you. So basically, we're just going to go to the definition. Okay, let's go to the definition of the Laplace transform. So we've got that L of f prime. It's going to be the integral from 0 to infinity of e to the minus st times f prime. Now, what we're going to do is we're going to basically partition this. We're going to break it into a bunch of little chunks so that we're integrating from 0 to, say, t1, all that stuff, plus an integral from, say, t1 to t2, plus an integral from t2 to t3, so on down the line. And just to help us out a little bit, let's just say that we're going to end somewhere. And then we'll take our limit when we go to infinity. Right? Because that's actually technically how we have to do these. So these are going to be our integrals of this form. Okay, so let's just think about what each one of these integrals is going to do. Now, we do have to integrate by parts because we've got multiplication going on. And so if we integrate by parts, what we're going to do is we're going to let the dv be f prime. So when we integrate that, we get v, which is just going to be the function itself. So if you look at that u times v bit, what we're going to have are a whole bunch of things that we can integrate. It's going to be e to the minus st times f of t from 0 to t1 plus e to the minus st times f of t from t1 to t2 plus dot, 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 dot. Right? So we got a whole bunch of those. And then we still have to do our integrals. The VDU part. And the VDU part is going to give us S e to the minus st times f of t. And then there's going to be another one, S e to the minus st f of t from t1 to t2 plus dot, dot, dot. So this is just a result of integrating by parts. Okay, so when you look at the integral of the e to the minus st, that's where this s bit comes in, or say the differentiation of it, and so on. All right, well, let's break this into the two pieces. Start with the bits where we're plugging in the numbers, so the definite integrals. Notice that the top of each one of these is the bottom of the next one. So the top gives us a positive value. The bottom is going to give us a negative of that value. So everything's going to cancel out, except for the bottom of the first one and the top of the last one. So if we go back and we look at what those were, right, the top of the last one is going to be A. So we're going to get e to the minus SA times f of A minus, plugging in 0, we get f of 0. So these two, they are what remain from all of the definite integral bits. Now, if you look at the other parts all have an S that we can pull out. So I'll do that. But then I can stick those integrals back together, right? So originally I broke them apart. Now I'm going to put them back together. And so that chunk, that was the other pieces. All right, so what's left then is to go ahead and let A go to infinity. All right, so let's look at what happens then as A goes to infinity. And we're actually going to work backwards. Let's go right to left. So if you look at that one on the right, if we let A go to infinity, so the S is still an S, but this other thing, that's the Laplace transform of F. So you may remember in the original theorem here, we had an S times the Laplace transform of F. Well, there's that piece. Okay, the F of 0, well, that's your minus F of 0. Okay, cool. That was part of this as well. So then what about this other piece? Well, that's where that boundedness comes into play. Right, remember for that bounded, I said that we needed to have a function that's bounded by an exponential. If it's bounded by an exponential, then we know that if you do the calculus on that, this is going to drop to 0. Because think about it, if it was just an exponential, then this thing is going to be an exponential as well, which as long as the exponent is negative will drop down to 0, and that's what that forces. We actually find that it's smaller than that, and a function that's less than a convergent function is also convergent. So that piece turns to 0. And there you go. There's our proof. So as long as your function can be, or is bounded by an exponential function eventually, then it will go away. And that's the linear, or the Laplace transform of the derivative. Whew. Okay, so a lot of nuts and bolts in there, but it really is just calculus. But we get to this fact that you can take the Laplace transform of a derivative really easily. Well, let's do a corollary to this. So remember corollaries, those are theorems that are related to other theorems. And the corollary to this guy would be, what do we get if we take the Laplace transform of the second derivative? Okay, well, basically we're taking the Laplace transform of this Laplace transform, basically, right? If you kind of go back, kind of extend it back, this is going to be, well, let's just build it. All right, so this isn't what it equals yet, but we'll build it. So it's the Laplace transform of the derivative of f prime. So by the theorem we just wrote, this is going to give us s times the Laplace transform of f prime of t minus f prime of 0. Right, just replace in here f prime for your f's. Well, we can also do the Laplace transform of f prime. So if I distribute, now this is your corollary. The Laplace transform of the second derivative is going to equal s squared times the Laplace transform of f of t minus s times f0 minus f prime of 0. So let me just kind of put a little box around that. So we actually know what the Laplace transform of the second derivative will be by going back to its original function. Well, obviously nothing's going to stop us from doing, say, a third derivative or a fourth derivative or a fifth derivative. And I want you to notice what's going to happen. Every time we take another derivative, we're going to have to multiply what was there already by s, right? Because that's what this says. So the next one will have an s cubed times L of ft minus s squared times f of 0 minus s times f prime of 0. So we always have to multiply by s and then subtract your new function. So the next one would have a minus f double prime of 0. Well, if you want the fourth derivative, okay, multiply all that by s, and then subtract the third derivative at 0, and so on. So you can even generalize this further and go to, okay, let's take an nth derivative. Well, you're going to get s to the n times the L of ft. And then each one of these, the multiple of s decreases by 1. So we're going to get like minus s to the n minus 1 times f of 0. The next one would be minus s times n minus 2 times f prime of 0. And I'm going to put minus dot, dot, dot. And I know I'm running a little bit low. Let me let me just back this up just a touch. Okay, so that's f prime. And then that's going to continue until the very last one is going to be minus s times the n minus second derivative at 0. And then the very last term doesn't have any s's on it. And it's going to be the n minus 1th derivative evaluated at 0. Anyway, so finding Laplace transforms of derivatives is actually not that bad. It really is pretty straightforward because there's a nice pattern to it. And it all comes from this original theorem that we just proved. But again, it has to be a nice function. It has to be one that actually works. But if it does, then you're good. Okay, so we're really close to actually using these things now. I think I'm going to stop here just because we're kind of at a good breaking point. And again, I don't want to dive in, but just to give you the preview where we're going, we're going to take the Laplace transforms of differential equations. We're going to solve for the Laplace transform of f of t. And then we're going to go backwards. We're going to use the inverse Laplace transforms to figure out what that original function is. Okay, so that's what we'll do on Friday, but I'm actually going to leave it here. So let me just switch screens real quick.
All right, so now you're seeing me. But like I said, we're basically building a tool, Laplace transforms a tool, that we're going to use to actually solve differential equations by way of algebra, which, yes, you may not personally like to have to do the algebra, and it will be gnarly. It absolutely will. But it is a way to get to solutions when we don't know necessarily what the function is. So that's what we'll do on Friday. So let me just pause here.